So hello, I am Dan Fithian, or dfithian on FP Slack, or I guess there were other things that I was dfithian, but I deleted almost all of my social network stuff, so if you try to tweet at me, joke's on you. Anyways, I work for T-Vision Insights in Boston. We are hiring, and I know in the abstract it said that all you needed was to know lenses and Aeson. So I apologize, there's also type families, which I didn't realize at the time that I was going to get so far into. So if that's really scary to you and you just don't want any part of that, then feel free to leave, but hopefully we can all stay and learn something. Cool. So first, some definitions. In Haskell, typically, most of what you see are called nominal types, types that have names. So you have two types that can have a similar structure within them, similar fields, but they're not equivalent. You can't define like a EQ class or that compares them. Conversely, row types are determined by structure and not by name. So in this example, the row type foo and the type bar. And I have my little laser pointer here. These two are the same, but these two do not have the same structure, obviously. Sorry, I'm not supposed to say obviously anymore. I didn't mean to say that. So first off, why are row types useful? Has anybody here, well, I know that you have used row types since you used the composite library, but has anybody else used row types in Haskell, Vinyl, stuff like that? Great. Well, the first question as to why we want to use them are, why are they useful? So the first thing is like set operations are easy. So if I have two types, I can extract the common fields between two types. I can figure out if one type is a superset, or one type's fields are a superset of the other type's fields. If all the fields in type A are a subset of all the fields in type B, and vice versa, then they are equivalent. So there's a notion of reordering in row types where you can just reorder the fields and you get the same equivalent type. And there's an example on that later. An example of something that's kind of like this already in Haskell are, so tuples don't have any real structure. They're not a nominal type. They don't have like a name. But they don't follow this ordering property. So like we said, value equivalence is easy. You can project fields out of one type or compare two types and extract the common fields between them. So for example, say you want to, for permissions reasons, you only want to show some fields in your UI or something like that. Like you can just extract the fields that somebody is authorized to see, and that's all great. You can add fields or merge fields between two types. It's kind of like inheritance, I would say. So if you want to say later on, we'll see an example where say I have a user who has a password and an email, password and username, but I want to add an email, then you can just lift the user type into some other type that denotes like a registered user or something like that. Cool. So there's this library, Vinyl, in Haskell that does a lot of this for us. It's this row type library in Haskell, and it's like an HList plus effects, where there are people who have given talks actually here at this conference on at least shapeless, I know, and probably other things of that nature. So I'm not going to go into HList, but except as sort of an example. But there's also this notion of effects in vinyl, which is really nice for composing sequencing operations. As you all know, you're here, so you know how good effects are. So what can vinyl do? It can do these subset operations. So there's a bunch of classes defined for the proofs of what fields are contained in which type and how you can sort of like reorder the fields to extract them. There's a bunch of lenses for actually doing the extraction or injection of other types or of other fields. And then we have functors for interpreting the records. If you want to follow along, those of you who showed up late, there was a slide with the repository. You can go to my GitHub page and then just clone the repo. So this first one is the vinyl example. All right. So first off, big scary code block. And we said not many people have experience with vinyl, so we'll just go through all this. The first way that we want to construct a record is basically this rec G80T. It takes something that's star to star, some kind star to star that takes U to star, which is going to be this F here, and then takes a type level list of U, and U is kind star. Sorry, anybody who's just like totally confused by what I just said, like kinds and stuff like that? Okay. Sorry, I probably should have put that in the abstract too. And then the output kind is a star. Cool, so it's just like a list. You have your nil constructor, which is a record of anything with a empty list. And then you have your cons operator, which is this weird colon ampersand, which takes something wrapped in my F and the tail of the record with that functor over my fields. And then I get a record with that functor over that field consed on all the other fields. Cool. So this example, we have type X. You declare the type that's going to be here, these U's. Character, integer. We can create a rec of the identity functor in X by wrapping each value in identity, consing it onto all the other ones, using this right associative property of the cons operator, and then this just says it worked. Cool, another scary code block. All right, this is where the type families are. So this is the first thing that we're going to do, which is proving that one field is contained in a type level list. So basically it's index. So index is what's the index of this field in this type. All right. So given an R, which is kind star, this K is star, and RS, which is a type level list of kind star, we're going to return, this is a type level function, returning a natural. The naturals here are defined, nat with the two constructors Z and S, where Z is just wrapped around S a bunch of times. So the index of R in the fields of R cons on to RS is 0. And this tick is the data kind, Z, which just promotes the data constructor Z to a type. And so that's the base case. So this says if I find R in this type level list, then my index is 0. So it's at the beginning of this list. If my R is not at the head of my list, I'm going to search in the rest of the list, and I'm going to prepend the S constructor onto the rest of the natural. So it's a recursive type family. And was that way too confusing for anybody? Raise your hand if you didn't get that. Wow, everybody just gets it. Great. Wow. Maybe all right, maybe we could just skip all this. I don't know. All right. Cool. This class for locating, defining a lens to a field in the type level list of our record. So this is like if I want to target a specific field, like extract. So I have like a thing that defines like a user. But this user has a bunch of fields. It has like username, password, email, address, whatever. But we're not allowed to collect that data anymore. How am I going to extract just the like email field? So this defines a way to, given a proof of the index of R in RS, I can give you this lens, which says that like, it says that I can extract R from the RS list, where this proxy will be erased, but we're not going to talk about it. And it will give you this lens into the record, and it wraps that functor around your field. And then I had some instances in here, but I didn't want to go over them because I felt like it was going to take too much time. So if you want to look at them, I promise, well, we'll see similar examples later when I go into how the composite library is defined. But they're all kind of similar approaches of using these recursive type families to kind of like locate the specific field that we want to extract. This type here is just a synonym. So it's the eta operator, which means like in math, it means this thing is in this set. So it's an element of this set. And we'll see an example of that in a slide or two. So here we have, again, our type X. We can wrap up our X in that same construction before. And then here's an example of using, here's eta right here. So we want to say if there's an int in our type level list RS, and given that RS, I can extract the integer wrapped in whatever functor I have. And that's just this obviously very, very simple incantation of view our lens proxy. So if we extract int on our X, we get that identity field that we supplied when we created the value. Everybody with me so far? Cool. Oh, yes?
Could you explain the I over our index?
Yes. This is type level quality, so you can just substitute this I here for this guy.
Okay.
Yeah. Cool. Another scary one. It's exactly the same. Images. Images are subsets of fields. So I want to basically iterate through a bunch of indexes of things and extract the subset of fields that I care about. So exactly the same if I have a bunch of fields that are kind star and a bunch of other fields that are also kind star, I'm going to return a list of naturals denoting each of the indices, and I want to say of RS in SS. So first one, inductive case, or base case, empty list onto SS is just going to be the empty list. And the image of R const onto rs in ss is the index of r in ss, which, as we saw before, is going to be some natural number, prepended onto the image of the rest of rs and ss. So recurse again through the type family. And then very similar type class. So given an image of rs and ss, I can extract the subset of RSs that are there. Is that the right way to read that? Sorry. Yes. OK, so it's another lens. We don't need a proxy this time. And again, if you dig into the code, that will become clear as to why. The instances are defined using the one level down, like iterating on the R-index and RLM class. Again, we have exactly the same operator, subset operator. So RS is a subset of SS if there's an image for it. Once again, we create our value x by wrapping it up. We ascribe this type. A is the type level list of characters. Project A says if A is a subset of RS, and I'm given a record of the functor f plus RS, I can extract a record of that same functor around A. And that's just view this R subset lens. And then right here, project A, we just project it and we get our character out. Cool. All good? All right. Equivalence. This one's just simple. It says what I said before. If you have two things that are subsets of each other, IS is just the list of naturals for the indices of RS and SS, and JS is the inverse. It's the inverse mapping of SS onto RS. Then they're equivalent, and this congruency operator is denotes that. So basically, the way that you would use this is essentially to reorder a bunch of fields within your type. So, and that's exactly what we have done here. So x prime is integer and then character. This is just reordering the fields. And so when we reorder x, where x is this, the capital X without the prime, and we want to turn it into a capital X prime, we'll just reorder the fields, and then we can reorder the reordering and get back our regular thing, or it doesn't actually do much if you just, you could call reorder X on the capital X type, and you could just get back the same thing, and it would just basically do nothing. Cool. Almost done with vinyl, I promise. I know there's a lot of big blocks of code here. So our traverse is a function that will take a traversal of all your fields and apply it to your functor, and you'll get that effect wrapped up. It's the same thing as monadic traverse, except you can do it on records. So this is saying, let's break this down. So it says, given a way to get from f of x to h of g of x, my record f of rs, and I will sequence my effect and get out h of record GRS. And trivially, your f can be the same as your g, as we'll see down here. So here we've defined two functions, just inside and just outside, which will basically sequence our effect in two different ways. Just inside will map over the f and stick a just under it, and just outside will just wrap up the entire thing in a just and give you the maybe type. So in this first example, this F is this F is the H, and maybe is the G. And conversely, here the G and the H have swapped, and the G here is the F here, and the H here is the maybe here. Cool. So when we call it, when we traverse just inside, we'll wrap up everything inside X in a just, and then the outside will be our identity functor. Similarly, if we do just outside, they'll be swapped. Cool. Finally, an example. Thank you all for bearing with me so far. So here's the example that I was talking about before. Essentially, if you have a bunch of types describing primitives for things you want to maybe share across other record types or something like that, say you have a username, a password, and an email, and then you have two different fields or two different types, but they share some fields, and what can you do to them? So another big scary code block, but this is one of my favorite things in GHCI now because I just figured it out and I really love it. It's called kind. So kind exclamation mark. And it will evaluate your type for you and tell you what it actually is. So I think if you say kind, usually it'll just like say, oh yeah, this thing is like a star or something. So this will actually, ascribe an actual, I don't know whether to say type or kind in this case. So I'm going to use them interchangeably, but it will give you the type of the thing that you're caring about. So we'll see a username is an element of a registered user, and it says, hey, yeah, the username is an element of the registered user, and its index is 1. Let's see. So username is in registered user, and this is 0, 1, 2. When we evaluate the kind of user subset of registered user, we get this cool, like user is a subset of registered user, and my indices are 1 for username is here at 1, and 2 for password is here at 2. So I think that's kind of cool. And then if any of you have read, there's that really awesome blog post called Typing the Technical Interview. Here's our runtime error of our type family being applied. Basically that says, I got to the end of the list and I couldn't find anything, so whatever, this index is like, I don't know how I would actually describe it in Haskell terms, but it'll end with the compiler saying, I couldn't find an instance of our subset for this thing. And then finally, we have our congruency operator. So we just reorder the fields in user to be password first, and then username. And the equivalency type just says user and user2 are equivalent. Let's see, it says that the index of username in user2 is 1, and password is 0. And the index of password in user is 1, and the index of username in user is 0. So, it's hard. Okay. Cool, so say we want to do something like validating a form or something. Some kind of example where you have a bunch of things and they might be true, and we only want to succeed if all of them are an actual value. So we want to say, like, to verify a single field, I'm going to take a maybe, and I'm going to wrap it in maybe of identity. And we're going to pass this function through our traversal, and we're going to traverse over all the fields in our user, and then we'll spit out either a user or some failure, where our failure will just be nothing because we're not doing anything complicated here. But obviously, well, God, I keep saying obviously. I'm sorry. We'll see later how this is a little bit more effectful in Composite with Aeson, but for here we're just going to spit out nothing. And so if we have a user, good user with who's provided all of the fields that we want, we can just wrap that up and we'll say, yes, I was able to verify this user. Here's the value, it's in this just. Or if I'm missing my username field, when we traverse and sequence the effects, we'll get back nothing. Cool. Recap. What have you learned so far? We've learned a bunch of proofs for finding type level lists of like natural numbers to figure out if things are elements of records. Similarly for subsets, similarly for equivalency operators. We figured out how to extract those fields or project a subset of fields. We've done some interpretation of effects, although we haven't done anything too crazy yet. But what is missing? And the first thing that you might have noticed is that this identity email thing is just so stupid. I don't know. It's just really pedantic. So I don't want to use identity and wrap all my values in identity anymore. And the other thing is that it can't use row types throughout our program because there's no way here to talk about how to talk to a database or parse any kind of data format like CSV, JSON, whatever. And I think at my company we were using row types a little bit to kind of do translations between database, say you have, we call it, I'm going to try and explain it, but basically you have like a fully hydrated type that's like in the database. So a fully hydrated type is a type that has all of its fields, all of its joins in the database table like populated. So instead of just having a foreign key, it will go look up the foreign key for you and populate it. So you get this big nested structure. If when you want to persist that to the database, you want to just extract the primary key field or the foreign key field, you can extract that. And this was really powerful for us, so we could do all this stuff using Vinyl, but it was constrained in this really weird way where we had a bunch of isomorphisms defining ways to get from our nominal types to our row types and back, and this was just, it's still pretty lame. We don't like using it, so for instance, if you want to buy into using row types, then we should be able to use them wherever we want in our program. So exactly what I just said, we want to define better operators and figure out a way to identify JSON keys or database columns using the previously defined row types and effects. Composite Records is a library that does exactly this. So it's a layer of syntactic sugar over Vinyl, and it uses a bunch of statically defined type identifiers. Known symbol uses that heavily, and it gives you JSON support, Postgres support, REST API support, and Swagger. A bunch of integrations that have not been written because you need to redefine them for basically every library, but the possibility is there. And so from now on, I'm going to show you first Composite, and then I'll show you the technique for implementing a library that uses Composite and how it can interface with something else like Opaleye or EKG or something like that. And then we'll do some JSON parsing. So here's our second example if you want to follow along. Great, so the first thing Composite does for declaring the syntactic sugar is, I guess before that, it defines this new type, which I'm just going to call arrow, but it's this arrow thing. It says we have a symbol, which is just a string, phantom type, meaning for those of you all seem to be following so far, so maybe this is pedantic for you, but symbol just means string, and phantom type means it doesn't show up in the right-hand side. So S arrow A is a value of, well, it's A wrapped in this value constructor. And then we have this star operator, which is the same as cons, the colon ampersand, but it will actually wrap something in identity, and it'll wrap it in your arrow new type, and you'll get your identity functor wrapped around each of your arrow fields in your type level list. Yeah?
Two questions. In practice, they use other things than identity. The identity seems to be the key here, right?
Right.
It's very convenient.
Yes. Well, identity is the one where it's just like I don't do anything.
Right. Do you use other starting factors?
Yes, we'll see that very soon. So in the previous slide, I was trying to show how to validate like a bunch of maybe fields. Maybe is not the most interesting functor, but there are other ones. So basically for parsing is what we're gonna look at.
And the other question is, well, record uses this neat trick of like a guided list, right?
Mm-hmm.
But you should be able to do a co-product type as well. So type level either. Do they have it? Can you like combine, record types with product types to get more sophisticated stuff?
That is a great question, and I haven't educated myself as to what a co-product is.
Well, like
in the vinyl library, there's co-record, which is what you're talking
there is, right? Okay. Cool.
Great.
Okay.
So yes.
Good, thank you.
Thank you. Our other pattern is the caret operator, which will, given a functor of your choice, you have to wrap the thing in your functor, but it will it will associate your symbol with your val and prepend it to your type level list. So essentially all this S arrow A business does is associate a static type identifier with the type that you actually care about, so that we can use it to look up like a JSON key. Here's our example. Exactly the same as before. Now we have just foo associated with our character and bar associated with our integer. We can construct a type way faster, no identities here, or we can construct a maybe record, and it will wrap it up in our arrow type. Then there's this template Haskell splice, which will define a lot of stuff for you. If you want to load this up into GHCI, I recommend it. There's some weird stuff you have to do to print the generated code. I think you have to use like string E. I think that GHCI only prints expressions as opposed to the EXP in template Haskell versus the DEC. But feel free to do that. It's kind of fun. Great. So that's the basis of Composite. It's pretty simple. All it does is associate a type with your value. Great. Now, the fun stuff, using Composite Aeson. So we're going to use this record type to parse JSON finally. And we're going to show that you can do it for JSON, and it's the most complicated approach of anything in the library. So you can either take my word for it that other libraries use the same approach, or you can look for it yourself. But there's these other integrations that we'll talk about at the end. Here's our example again, if you want to follow along. All right. So first thing, we have this other library called Aeson Better Errors. If you haven't used it, please do so. It gives you errors that are better than the regular Aeson library. We basically define this from field functor that's going to have this error type on the left and a success type on the right. Same thing as your either type. And it's going to take some JSON key and return a parser for that JSON key that fails in E and succeeds in A. And then we're going to declare a type class that says, given a bunch of these from fields, so from field E, where E is our error type, and a type level list of fields. So this is like positional, right? So like it says that for each field in RS, we have this from field thing in the record. So it's going to define, once we wrap it all up, you'll have a way to parse the first element of your record type cons onto a way to parse the second element of your record type, cons onto the third one, et cetera, et cetera. So past that, we're going to be able to parse failing in the E error type, and we'll pass back, if it succeeds, this record. So this gets at your question is, what else can we use it for? So if you notice, if you squint, you can see that we're going to be using our traverse, or any applicative instance to take this inner parse and wrap it on the outside. All right. Well, how do we parse nothing? It succeeds. Great. So when I want to parse the empty row type, I just return that. Great. Here's a really hard one. All right. Here's our inductively defined type class that is, or instance that is, you're going to see throughout the rest of Composite. Really dense, I'm sorry, but I hope you'll follow along. This just says, given like an identifier of our S type for S arrow A, and a way to parse some list of, given a way to get a record for this type level list, I know how to parse S arrow A consed onto RS. So basically, it's inductively defined. So we're going to parse the first element and then recurse and parse the rest of the elements. So that's exactly what it says here. This A from field is our this function here. So I'm going to pass A from field the JSON key that we care about. So this is like for, I guess, what did we have before? I have to go back. Right, here. So it's foo, or bar in this example. And this just wraps it up into a nice text format. I'm just going to parse that field and wrap identity around it. This is the applicatively applied cons operator from Vinyl, if you remember. So we're just going to map It's a sequential application, just like, I don't know, has anybody not seen this pattern before? Cool. And so once you have parsed the first field, you can go and parse the rest of the fields, and they will end at the empty case. Great. So let's parse some stuff. So same example as before. We have a user that we want to parse. It has a user field, a password field, an email field. This is just a helper function that will give us a way to parse. Given a key X, we'll just use our Aeson better errors library to parse the object at the key X as a text. And so positionally, as we said before, here we have our username parser is here, password parser is here, email parser is here. So they're positioned inside the record based on which field we care about. And when we pass all this through, yay, we'll be able to parse a user from from JSON, and we get record types right at the boundary of our program. Yeah, so I thought this was a really nice result, and using Aeson better errors gives you these nice error messages. So if you, for example, omit your email key, you'll get this key missing error, and likewise, if you change the type of your user to be an integer, you'll get a similar error message. Okay. Another recap. So whereas in our first recap when we talked about vinyl, we had all that good stuff of proofs and extraction and effects, and now we've given vinyl some syntactic sugar, some static identifiers for our types, and we have defined some type classes for parsing JSON. And if you go look in the Composite GitHub, you will see integrations for these other libraries, for Opaleye, for EKG. For those of you who don't know what EKG is, it's a way to collect metrics about your service. And Swagger. Swagger, for those of you that don't know, is a way to define like a spec for how, like the API surface area of your service, and then you can generate like a client in different languages. So personally, Servant has its pros and cons. One thing I really like about Servant is that you can define a Swagger spec for it really easily. And so there is a composite integration to do this in the same way. So if you happen to define a Servant API with a bunch of row types, then you can get a Swagger spec for it too. And then here on this last page, we have our resources. So all these libraries, and the final one, if you want to go look for it, is an actual example of all of these libraries in action together. Cool. So thank you for listening to my first talk ever.